Welcome back, Math 170. We're going to hit up 3.7 optimization problems. And if you're wondering what that really means, optimization, pretty much we're looking to maximize or minimize equations that we're going to be building from these word problems. And the idea, we need to read the word problems very carefully, and we want to extract functions from these word problems. And some of them are nice and straightforward, and some of them will require a lot of work. So I have about 7 examples to give you experience. It's really impossible to lecture on every single type of example that you're going to come across. But hopefully with these 7, you'll have an idea of how to approach things. And hopefully you'll see that there's some of them have trends. So we'll start off somewhat nice. It is possible to do these, some of these without calculus, but I really want to tie in the first derivative, second derivative to this situation. And for the most part, we will be expecting you to use calculus to find these values unless the functions are incredibly difficult, like we were kind of seeing when we were trying to take the first derivative from the last section. I think it was 3.5. But I believe I'll be able to show you everything in terms of calculus for these. So let's get started. We've got to find 2 numbers whose difference is 1,000 and whose product is a minimum. So what I'm always looking for is the words minimize or maximize, and I see it right there. So what I'd like to do is always kind of state to myself, what are you trying to optimize? And in my case, when I'm reading this, we have to minimize the product. So when they talk about 2 numbers, we want to see if we can identify variables to help us out. So favorite variable x, let that equal the larger number. They never assume that these numbers are equal. So we need to not make that assumption unless they tell us. So I have x equaling the larger number, y equaling the smaller number. So if you're trying to figure out what you have to minimize, a lot of times it's saying, okay, what does it mean to take the product? Well, a lot of you are saying, oh yeah, x times y. But the issue with trying to minimize something that has 2 variables is we are single variable calculus. So our goal is to define whatever we're trying to optimize as a function of a single variable. And keyword being single variable or single. The idea is to try to extract information from the problem and maybe ask yourself, is there a relationship between our 2 variables? In our case, it's between x and y. And I kind of read into it and I say, well, they did mention that the difference is 1,000. So we have this idea, difference is 1,000. And we weren't trying to minimize or maximize the difference. This is just kind of our secondary equation to help us. So if the difference is 1,000 and we want to make sure it's a positive number, that would make sure that we'd have the larger number first, subtract off the smaller number to give you 1,000. Well, now you definitely have a relationship between the 2 variables. So it's kind of like using substitution to help you figure out what you're trying to minimize. So I'll take this secondary equation. Sometimes you don't really have to You don't really have to refer to it this way, but you have to always keep in mind whatever you're trying to optimize. And sometimes it's easy to lose track when all these complications are happening. So we're going to take the secondary equation and see if you can solve for one of the variables. It really doesn't matter, but to me, I think it's a little easier to add y to both sides. So I have everything in terms of x. X equals y plus 1,000. So what we want to do is go back to the product, which in our case, we said it was equal to x times y. And it's a good idea to do substitution to make sure that everyone's in terms of one variable. So we just figured out that x was equal to y plus 1,000. So we can substitute that in. You probably already guessed, yeah, no problem, we can do that. And at this point, you can look at it and say, well, let's just simplify it. Distribute that y, so we should get y squared plus 1,000y. And keeping in mind, we're trying to minimize it. So a lot of times what they like you to do, we already kind of know what we would be maybe dealing with the calculus. And sometimes when we were in pre-calculus, we used to say, oh, product, we'll call it P. Well, that's fine. But a lot of times they like to define it as a function of y. So we like to use function notation. So instead of P, they'll use F for function. And they'll say, well, what are we making it in terms of one variable? It's the y variable. So all we're doing is defining it as a function of y. And if we had solved for y in the secondary equation, then we would have a function of x. So it's whatever you're doing in the secondary equation that kind of designates what's happening in this, what we call, sometimes you refer to it as the primary equation. Primary, basically, what are you trying to optimize? And if we are trying to minimize this, we're probably going to be looking at finding the derivative, because that kind of gives us a heads up of where we might have a local min. So we're going to try to do that. And that's going to be the trend of a lot of these problems. Well, I'll take the first derivative. So if we look at the derivative, I should write that a little prettier. So we're going to look at the first derivative and see what we can come up with. So we can do that. The derivative of f with respect to y, it's a nice polynomial. So we should have 2y plus 1,000. And a lot of times with these optimization problems, right away we know we're looking for critical numbers. We know polynomials are never undefined, and the derivative is a line, so it doesn't look like it's ever going to be undefined. So we're going to set it equal to 0, and then we're going to solve for y. So we've done this with the other functions. We just didn't have anything to apply it to. Subtracting the 1,000 from both sides. Now we divide both sides by 2, and we get y equals negative 500. Now here's the main part. In terms of getting full credit on a problem, we already know it's a critical number, but we want to ask ourselves, is this a minimum? Or how do you say, formally, is it a local minimum? And so you would have to prove this. We prove this with calculus. And in my case, what I like to look at is that when the first derivative is not too complicated, the second derivative test is usually more convenient. And what I'm looking at, if I'm using the second derivative test, little note to myself, I'm looking at the derivative. Okay. So derivative of the first derivative, we would have what? Just a 2. Now, if you're using the second derivative test, you're substituting your critical point in for y. So you'd be saying, okay, let's look at this. Critical point was negative 500. Well, our second derivative had no variables, so even if you plug in negative 500, you're going to get a 2 back. And what we're looking at is that second derivative evaluated at the critical point, is it greater than 0 or less than 0? Well, it happens to be greater than 0. So what happens? That's the second derivative test. They're telling us that the function evaluated, the actual function evaluated at negative 500 is a relative min. Or I could say local if that's something we're interested in. So this is necessary. A lot of times you'll kind of notice that when they ask you the question, it's assumed to be, but please show that so that you can get full credit. So run through it. And you could have also used the first derivative test, but that would apply you testing signs on both sides of the negative 500. And it's not too bad, but it just takes a little more time depending how complicated your function is. So we have verified that it is a minimum. So the last thing we have to do is answer the problem. So answer in the context of the problem. We found y equals negative 500 was the smaller number. So if we want to find the x, we plug it into our relationship, and I think x plus y was equal to 1,000. So x was equal to what? Y plus 1,000? Was it x minus y equals 1,000? Let's look. Yeah, the difference. Okay, so then we had solved for x equals y plus 1,000. So that's negative 500 plus 1,000, which then gives us x equals 500. So that's a little bit of work there. Therefore, if you're going to answer the problem or circle your final answer or restate it in context, a lot of people like complete sentences. The numbers are, not and, they are 500 and negative 500. They will give you a product that's a minimum if their difference is 1,000. So see the trend. First idea is to kind of look at, one more time, figure out what you're trying to optimize, whether it's a maximum or minimum. And once you do that, if you can extract a function from it, sometimes that function is in terms of more than one variable. So you need to use another relationship in the problem to rewrite so that you can take your primary equation and turn it in terms of one variable. And that's where we were looking at right here. Now, once everything is in terms of one variable, you can then use calculus to test or check if you have a maximum or minimum. Don't forget, always show and verify if you actually have a maximum or minimum, because sometimes the problem will give you something you don't need and then you have to go back to the drawing board. So don't assume, always show. So now that you kind of have a feel for this, we'll step it up a little bit. And we'll start off with a farmer having 700 feet of fencing, and they want to enclose a rectangular area subdivided into 4 pens with fencing parallel to one side of the rectangle. So you have to kind of think about what this means. More than one way to look at it, but we talk about one side of the rectangle. I assume that you just pick one of the sides. I could have probably make them the other way around. But for purposes of the problem, I threw a rectangle down on the paper to get my gears in my brain moving. And I want to understand that they want 4 pens. So if they want 4 pens, they have to make 4 subdivisions, or excuse me, 3 fences. So they didn't specify, they didn't say that they're going to be equal sizes. So we don't know. So we can say something like this. Let's see if I do another one. That's going to be 3 pens, so maybe one more. So we don't know what the farmer is housing, so maybe it's garden, maybe it's animals, who knows? But they didn't specify that it's equal sized pens, so I just drew them how I thought. And what I'd like to do is try to relate this to variables. And a rectangle is our favorite shape in mathematics, mainly because we know some properties. The sides of rectangles, what do we have? Length, usually is the longest side. And then we talk about width as the shortest side. And we know that opposite sides are equal. So we do have a length up here and a width over here. And we could also assume that if the fencing is parallel to one side of the rectangle, probably the length of this first fence is also W. This second fence, also W. And this third fence, also W. It kind of gives us an idea of what we're looking at variable-wise. So I wanted to make sure I kind of understood the situation before I decide to just set up an equation. So I'm going to read one more time, make sure what I'm trying to optimize. This time around, they ask, what's the largest possible area that the farmer can enclose? So they never said maximum or minimum, but we know enough when we see largest, we know, oh yeah, that is maximized. And the question is, when you talk about geometric shapes, there's a few things you could be identifying. Are you looking at area? Are you looking at perimeter? And they ask us about area. So the idea is just kind of a note to yourself. We need to maximize the area. And as long as you know that, then what happens is you can also come up with, well, if you know what the shape is, we know we have a rectangle, so area of a rectangle is length times width. So we know we're going to be working with that piece, but before we can even work with it, it has to be in terms of one variable. Right, Leica? Right. So just kind of a little note. So right now it's in terms of length and width. So then if we are looking at this, I have to use another relationship, and lucky for us, they talked about fencing. So we're going to go into that. And let's look at that secondary equation. So total fencing, we can't just be stuck on the fact that we're dealing with a rectangle. We're not just dealing with the perimeter, we're dealing with the edges as well, the fences on the inside. So if I'm looking at my fencing, I'll see if I can highlight so you know what I'm talking about. I definitely have two of the lengths. You're trying to keep whatever it is in or subdivide it out. So that's where I'm getting my 2L. And then when I'm trying to figure out what else I'm looking for, I need the other side. So then I have my W. Not just the edges or the perimeter, I'm also looking at here as well. So that's 1W, 2W, 3W, 4W, and 5W. So it's a little different than how we're used to maybe from our what is it called? Pre-calculus. Don't assume. But they also told us like what the total fencing is. It's not a perimeter. They told us that it's 750 feet. So I kind of have that relationship now. And then I decide for myself, well, I have a choice of solving for L or I have a choice of solving for W, and it's totally up to you. I just see that the L came first, so that's what I'm going with. So I can move the 5W over. This will kind of give me an idea. I have 2L equals 750 minus 5W. Now you can divide by 2, however you'd like to do this. I noticed that 750 minus 5w, I can do it this way. (750 minus 5w) over 2. But sometimes there's more than one way to play with it. Some people like to further reduce if they notice, instead of making it one fraction, they might say that, oh, the 2 is a monomial. We can break this up where it's 750 over 2 minus 5w over 2, and then divide. So we use a calculator. 750 divided by 2, 375 over minus 5 halves w. Either way, any of the forms will work. It's just an idea of like, what are we trying to do? We have to eventually plug this back in. So kind of keep in mind, you decide what you solve for. In this case, we solved for one of the variables, it was L. So the reason why we had to go through that all is because we're trying to maximize our primary equation, the area. So if I solve for L, then what I'm going to have to do is take and plug back in. That L was 375 minus 5 halves w. And my w was still there from the original idea of what is the area of a rectangle, just so that you see that. And now I know you can still call it A, but a lot of times if you want to be a little more proper, you're saying area is in terms of what dimension? It's in terms of the W. So it's a little bit of a more professional way to approach it. If you want to call it A, no problem, we'll still understand it, but it's nice to define it. So now, if you're trying to understand what we're looking for, remember, we're trying to maximize the area. So when we're trying to maximize the area, this would involve us probably taking the first derivative. But when I look at the area right now, I see that it's a product of two functions, but it's a binomial times a monomial. So I prefer to rewrite it, maybe make it a little prettier, so that I can maybe distribute the W through. That will be a little nicer for me to take the derivative. So that's why we made you go through chapter 2, so you find nicer ways to do things. Feel free to use the product rule. You're still going to get the same answer, just a little longer. But the idea, again, if we are maximizing, we are going to try to find the critical number. So we want to find the derivative of A with respect to W. So if we do that, we should get a 375. Now we're taking the derivative of a squared term. What do we have? 2 times 5 halves. The 2's will divide out, so we get negative 5W. And now remember, we started off with a polynomial, so there's not going to be a case where the first derivative is undefined. So this is the case where we're setting it equal to 0 to find that critical number. And it's a nice linear equation to solve for W. So if we solve, I believe we can move the 5W over and get 375 equals positive 5W. Divide by 5 on both sides, we should get W equals 75. And if we kind of go back and we're like, well, 75 what? Probably feet. So that makes sense according to the problem. Yeah, we need to get something positive. But the next question you have to ask yourself, and you want to be clear about this, is this a max? And you can assume probably yes, but we need to show this. So this is the case where I might take the second derivative. Now the second derivative of the area, that will just be a negative 5. And then when we're using the second derivative test, if you plug in your critical point, so I kind of like it if it's easy to take the second derivative, or easier. If you plug in that critical point, there was no variable to begin with, so that was kind of quick. Still negative 5. And you're just testing for yourself. Is that going to be positive or negative? And you know it's negative, less than 0. So what you have at that point, what does that tell you? The area evaluated at 75, if it's less than 0, we've got a local max. Or sometimes they say relative max, because we use those words interchangeably. So now we kind of verified it. Don't forget, show this. Get credit, full credit at least. So we have a pretty good idea that this width at 75 feet should maximize the area of this pen. So answer the problem. And always try to answer it so that you are the one translating the English to math. Now, they're not specifying what width, they're asking what is the largest possible area the farmer can enclose. So the answer would be addressing this. The largest area, let's go back to when we set up area, what was that? 375, or A, evaluated at W equals 75. And just so that you know what I'm looking at, we're looking at the area. So if we want to plug in, we have A, whoops, here we go. 375 times 75 minus 5 halves times 75 squared. Do a little bit of math with your TI. What do we have? 375 times 75, we'll type that in. I should have, there we go, 28,125 minus 5 halves. 75 squared is 5,625. Simplify a little bit. I know we can do this on our TI, but I want to make sure. I have to take 5 halves times 5,625. I'll do that with my TI. So we should get a decimal. It is reasonable, 14062.5. Then when we do the subtraction, oh, that's interesting. We have positive 14,062.5. So when you find your answer, remember you have to address it in terms of the words of the problem. So yeah, area 14,062.5, but we might want to say, well, what does that mean? What we were in terms of feet, so area is measured in square feet. And if you want to rephrase it, that's usually what we're looking for. The maximum area that can be enclosed is 14,062.5 square feet. More than one way to do that. But that's what makes you the big bucks. If you can translate all of this mathematics into a nice sentence involving the context of the problem. So you're starting to get the hang of it. Okay, so let's play with example 3. And let's take a look at this problem. We're looking at finding the exact coordinates of the points. Oh, so they don't even specify. It could be 1 point, it could be 2 points, 3 points, who knows? On the curve, 4x squared plus y squared equals 4 that are farthest away from the point 1, 0. Okay. So what we're looking at, we have to probably draw a picture. I'm thinking to get an idea of how this situation will be. Let's see what we're looking at first of all. The curve. I see 2 squares, x squared, y squared. And I remember from algebra that this is a conic section. And I don't think it's a circle, so I'm going to see if I can rewrite it so that's equal to 1. So if I divide both sides by 4, that's going to get me x squared plus y squared over 4 equals 1. And I do have an ellipse. That's why all the algebra comes back to haunt us a little bit. And then a lot of times if you're thinking about it, what we need to understand, the ellipse is, the orientation of the ellipse is designated by who has the higher denominator under the squared term, and looks like the y does. So we actually have ourselves a vertical ellipse, meaning it's elongated this way. But we'll see when we go through it. And a lot of things we can understand if we're trying to go through this. The center, it's very nice. It's centered on 0, 0. And then that kind of gives us an idea of the way we've defined conic sections in our past, that our A is associated with the denominator, and the B is associated with the denominator on the X. Feel free to review that. But what I need to do now is graph it. And lucky for me, I have graph paper over here. I guess I don't have to, but we'll draw it larger just so that we can see what's going on. And if I'm looking at my ellipse, I'll exaggerate it a bit, make this in terms of ones. So every 2 tick marks. Okay, so the center is 0, 0, good there. Now if it's longer vertically, we're going to count 2 units up and down. That's going to give us our vertices of the ellipse. And then left and right, that's our co-vertices. So now we actually have our ellipse. Pretty good there. Okay, now if we're trying to understand what we're looking for points on the ellipse that are furthest away from our point 1, 0. So let's mark where that's located. It's actually on the ellipse. So that's the point 1, 0. So what are we trying to find? Anyone that's located on the ellipse, their distance from 1, 0. So let's say we take the top vertice. If you calculated that distance, we're looking to see if that is going to be longer. Then maybe if you took the distance from 1, 0 a little bit more on the left. Or maybe you took the distance from 1, 0 to the co-vertice. Or how close do we have to be? So there's many options. These are all the possibilities. Well, if you have possibilities, too many possibilities, and just by eyeing it, I don't know, I wouldn't be able to tell. You know, I'm guessing it kind of might be closer to the co-vertice to co-vertice, but we can't be sure. So what I want to do, we're maximizing, we're not minimizing, right? Farthest away. Okay, so just kidding. We will cross that out. That's probably the closest distance. So I wouldn't be able to tell, you know, would it be this distance or this distance? They look pretty similar to each other. So this is what we're going to have to do, is use calculus to help us out. What we want to do, farthest away is key for maximizing. We're going to want to maximize the distance between 1, 0 and some point on the ellipse. We do not know what it is yet. We have a guess of what they could be, but we'll see. Okay, so then this is where we have to bring in what do we know about distance? Distance of 2 points on a line segment. And here we go, pulling in something from our past. So we're going to use the distance formula. That's why when you do a lot of them, you'll have more to pull from. And if I remember correctly, the distance is taken, it's kind of like has to do with a right triangle. So that's where the square root comes in. And we're taking the distances from each of the points, the x values of the points. So in our case, x1 minus x2, so I could put the x first. So I have x minus 1 square, add that to y1 minus y2. So we say that, y minus 0 square. Feel free to verify that, but let's clean it up a bit. I have x minus 1 square, and it's kind of nice, the y minus 0 square is just a y square. Now remember, if we're trying to maximize the distance, then our goal is to get it in one term, terms of one variable only. So then you do have a choice. We are looking at it and we're saying, well, we can either put it in terms of x's or in terms of y's. And the first thing I want to do before I even try to make that decision is let's look at the relationship. What is the relationship between x and y? They are related by an ellipse. And that formula is 4x squared plus y squared equals 4. And so what I'm looking at is this secondary equation. I could have looked at it where I solved it so I can graph it, but I like this one better. What's more efficient? Is it easier to solve this for x or y? Or when we look at what we have to plug in anyways, I mean, if we have to substitute in for y squared, it might be easier just to take this in terms of y squared instead of x or just y. So I would take this, solve it for y squared. So that gives us subtracting 4x squared from both sides. See if I can erase it. So 4 minus 4x squared. And now I can take that and substitute that in to my distance. So if I do that, I have x minus 1 squared. Now instead of y squared, it's going to be 4 minus 4x squared. And now, if we're going to be formal about it, we have everything in terms of one variable, and that one variable is x. So now we can write the true function notation, distance in terms of x. And my advice to you before we even go forward is I would try to clean up the radicand. Yeah, because eventually we're going to take the derivative. It might be nicer to see what we get on the inside. So let's take this, clean up the radicand a little bit. Maybe we can do that by squaring the binomial. X minus 1 squared, x squared minus 2x plus 1. What do we have? 4 minus 4x squared still, plus 4 minus 4x squared. Oops, make it a square, not a 2. There we go. And we do have some like terms. Okay, we'll go with it. So x squared minus 4x squared gives me negative 3x squared. Don't have any like terms with the negative 2x, so I'll keep it there. But 1 plus 4 gives me 5. And now, I mean, it's a little prettier. I feel a little bit better about this. Remember, if I'm trying to, what am I trying to maximize again? I'm trying to maximize the distance. So here I go. This will involve me now trying to take the first derivative. So I'm going to find the derivative of x, derivative of the distance with respect to x. But before I find that, you notice how you had a radical? You can always rewrite that radical. That's a square root, so it might be better just to rewrite it so it's a power of 1/2. See how I don't always know what I need, but the minute I noticed I had to take a derivative, I don't like square roots or radicals when I take derivatives. I like rational exponents. So now it's a little nicer for me. I can move the 1/2 around to the front. I can, remember it's a chain rule, so 1/2 negative 3x squared minus 2x plus 5. If we are subtracting 1 off the exponent, that's negative 1/2. Well, remember the chain rule, we're going to have to attach on the derivative of the inside. So derivative of the inside is negative 6x minus 2. Now, eventually, remember, when we want to, the reason why we were finding the first derivative is to determine if we have a critical point. So eventually, we're going to see if we can make this equal to 0, or we can determine where it's undefined. So maybe before we even do that, let's look to see what kind of final format we have. So I noticed I had a negative 1/2 exponent. So I'm seeing maybe it's a little nicer to look at it where I rewrite the negative 1/2 as positive 1/2, but then that's moved to the denominator. And I should have a negative 6x minus 2 on top. So that's kind of a little nicer to interpret it. Whenever you're trying to find critical numbers, usually has to involve you setting it equal to 0. But we want to be careful because we have two options here. The derivative is equal to 0. We got a fraction going on. So derivative is equal to 0 when the numerator equals 0. It's one of the nice shortcuts. And so that's kind of nice. You don't have to deal with the square roots at the moment. And so our numerator was negative 6x minus 2. Oh, that's beautiful. Solving. Let's see, we have negative 6x equals positive 2. Divide by negative 6 on both sides. We should have 2 over 6, so negative 1/3. Okay, so we do have a critical number. Before I even care about it, I'm going to want to verify if it's a max or min. So kind of make sure you have a note to yourself. Verify if a maximum or min. We can do this now, but remember, I had an issue because when I'm looking at my derivative, it's a fraction. So I don't want to just stop there. I need to find all of the critical points. And so there's a second issue that we have to understand is when your fraction is undefined. So your distance is undefined when your denominator equals 0. So if that is the case, let's look at what our denominator is. That's, we got a radical. But let's see where it takes us. So that's equal to 0. And what's kind of nice is the 2 can divide out. So we end up getting the radical is equal to 0. Then if we square both sides, at least that lets us get rid of the radical. That's nice. And now I get a trinomial. And a lot of times if I see a negative x squared, You may be interested in maybe moving everyone else to the other side or dividing out by -1. So sometimes it's nice to see a positive x squared term, but it does reverse all the signs. And then I'm hoping this factors. Factors of -15 that add up to 2, it does factor. We can factor that add to 3x plus 5, x minus 1. And so that's going to give us 2 answers. We have x equals -5/3 or x equals 1. And again, we have 3 critical points we're going to need to verify. We can't just make a decision right now. Verify if we have maxes or mins. So what I'm noticing when I look at this, whenever I have to verify, I'll move over a little bit. The last 2 examples, our first derivative, kind of go back a little bit. When we were finding the first derivative, those were nice polynomials. So it was pretty quick to find a second derivative. Even when we look back here. First derivative, nice. Second derivative is pretty nice to find. I'm a little nervous about this one. The first derivative is a rational function with a radical in it. And to me, it might be a little rougher to take that second derivative. So I might go back with the idea of first derivative test, finding intervals of increase and decrease. It's totally up to you, whatever you find more nicer, but my opinion, I don't really want to take the time to find the second derivative of something that's a rational function that has a radical in the denominator. So I'm going to use the first derivative test. That's why we taught you more than one test, because depending on the ideas that you get for your functions, one's nicer than the other. You know, maybe you like taking derivatives though, so either way. So what I'd like to do for myself is first derivative test, pretty much I'll make a quick little idea of a number line and kind of referring that I'm looking at the first derivative, d prime, and I'm going to plot all of my critical numbers on that number line. So if we do that, let's see those critical numbers. Let's look at this one more time. We had -1/3, -5/3, and +1. Okay, we can do this. Put them in relation to each other. -5/3 probably is more to the left, and we have -1/3, and then a 1. Maybe not to scale. So this might be a case. Again, we're looking at our first derivative. This might be a case where I'm using my TI to plug this in. So I have a table of values that might be quicker. Let's pull that up. I know we could do this by hand, but we have a lot of other things to deal with. So let's plug in our first derivative, -6x minus 2 divided by, and be careful with everything. I want to make sure that everything is in terms of the denominator. So that 2, I'm going to enclose. So 2 times square root of -3x squared. Nope, we're still in the first y1. Come on. Okay, -3x squared minus 2x plus 5. And then close off that denominator. So make sure you have a clear numerator, a clear denominator. So my first derivative is entered into the calculator. So now what I can do for myself is go to the table, might be a little faster, and enter numbers on each boundary. So for example, someone on the very left boundary, to the left of -5/3. Negative 5/3. If I were to have a decimal, it's about negative 1.6. So let's say negative 10, just to be safe. Can we do that? Are we defined there? Oh, we should probably press equals. That might be something. Try this again. Let's do -2, getting an error. All right. Why is that? Maybe we're undefined, perhaps. That could be an issue. Let's see. So let's do -3. See if that gives us anything. I'm getting errors. So I'm having a feeling that we're maybe undefined. We'll see if we can find something on the other side of 5/3. So maybe we'll say -2/3. See if that gives us anything. We're getting a positive. Maybe I just have to go a little closer. Okay, we'll go with it. Let me mark my sign. Let's go back to my number line. So I know the first derivative is positive on this region. And I'm still kind of eyeing this one. Let me try out -5/3 one more time is about -1.67. So it's reasonable. If I go back, I know I have a negative on top. We could do it this way. Let's think about it. The calculator is giving us inconclusive, right? Maybe we're just picking too far. Let's see. Let me think about it this way for you, just because sometimes it does fail us. Okay, if I were to factor a negative out of the numerator, that's 6x plus 2, 2 radical square root. Now, the square root, no matter what we get, is always going to be positive. So we're okay there. This 2 in the denominator is always going to be positive. Nothing has changed. So I need to understand what's happening here. So if I were to pick a number on the left of the -5/3, so I think -2 is okay to pick. What would happen? 6 times -2 plus 2, -12 plus 2 gives us all of that turns into a negative. So now we have negative times negative, which gives us a positive. So sometimes the TI kind of failed us, but we can think through this. Radicals, remember, square root of anything, it doesn't matter. The inside's not supposed to be negative. That's probably why it's undefined. That's where we're getting that. I should have thought of that before, but it's okay. We work our way through it. So right away, I already know if I'm trying to deal with, do we have a critical point or not, or max or min? If I'm going from positive to positive, my distance is going from increasing to increasing. So that this must be a vertical asymptote or something like this. Maybe it's a hole, but I already know right away that -5/3 is not a max or min. So you see what I can do is I can get rid of this into consideration. Now I want to go with 1/3 and 1. Let's see if our TI will help us. A number in between -1/3 and 1, 0 is a great one. And then number after 1 would be maybe 2. Let's see what it gives us. And if not, we have to just go back to the drawing board. Here we go. So what was I picking? A 0? That's a negative number. And I believe if we go beyond it, we should probably get something that's undefined, I'm guessing. So if I pick a 2, that's where we're getting another error. Let's see. We can do that test again. You should probably see what I'm seeing, so just in case you missed that. What I did is I plugged in 0, and I got a negative number. Then I wanted to plug in 2. That's the region beyond +1. And I got an error. So I'm guessing I have some undefinedness going on. And I'll test it out when I go back. Okay. So rephrase, got a negative. So now we're decreasing here. So right now, if I'm going from increasing to decreasing, increasing to decreasing tells me that I've got myself a local max at -1/3. But I just want to test out what's beyond the 1, just in case it ends up being positive. So let's see if it gives us anything. So same reasoning. I'll erase all the extra stuff so we see. We already know the denominator is positive. Now, we already know we have a negative sign. So if I pick something beyond +1, like 2, this part right here, 6 times 2 plus 2 is going to be positive. So in the end, we're going to have a negative. So notice your function, decreasing to decreasing. There's no local max or local min. So lucky for us, we only have 1 point to kind of really understand this. So took a little while, but we were able to do this. Right now, I'm probably gonna use more space out here. From this work, we see that it went from increasing to decreasing at x equals -1/3, and I'll specify that as that was our derivative. So our f prime, well, it shouldn't be f prime, it's d prime, according to what we're talking about. So that's telling us there is a local max where x is equal to -1/3. So let me go back, and I'm feeling pretty good about this, but what were we trying to find in the first place? We were trying to find the exact coordinates of the points. So we have an idea at x equals -1/3. If I can go back to my picture, at x equals -1/3, whatever that y value is, which is about here, the distance from 1, 0 to that point is the winner. But my friends, at x equals -1/3, there's also another point on the ellipse that also counts. So in purple, we're looking for what are those y values. We already have the x value for both of them. We just need to find what those y values are, and by symmetry, we're probably guessing. So let's go back, just so that we understand this. A lot of times you have to look at the picture. So if we're finding the y, okay, finding y, excuse me. If we're doing that, we're going to our relationship one more time. We already had y squared. Y squared solved in terms of x, it's 4 minus 4x squared. And we already know what x is. Y squared equals 4 minus 4 times -1/3. Don't forget to square it. A little bit of math here. A little bit, a lot. So 4 minus 4. Now 1/3 squared is what, 1/9? We still have y squared. Maybe with the help of our TI, what do we have? 4 minus 4/9. So 4 minus 4/9, save all the complications for your algebra and your calculus in your brain. Let's use our TI to help us out. So 4 minus 4 ninths is 32 over 9. But we have to take the square root of both sides to figure out what's the actual y value, and don't forget the plus or minus. So let's verify this. Square root of 32 over 9, if you want to be pretty about this. A lot of times square root of 32, we would simplify. 32 is 16 times 2, so 4 square root of 2 over 3. So my friends, we have our points. We just got to scroll back and find out what they are. 4 square root of 2 over 3, that's the particular y value, and the plus or minus, yeah, that makes sense. It stands for the positive case and negative case. So if we're going to answer our question, finally, so the points, they were specific. They didn't just want the x value. There's x equals negative 1/3. There's the 4 square root of 2 over 3. And the other point, still negative 1/3, but the y value is 4 square root of 2 over 3. Final answer to our question. Wow, look at all that math we did. Went off the paper, mainly because I write big. But look at all that. Come on, you can impress your friends now. But really, the understanding behind all of this, we're looking at what we were trying to find in the first place. If we didn't know we were looking for a distance, we wouldn't be able to go this far. So while you're kind of thinking about this and feeling a little bit overwhelmed sometimes when you see all this writing on your page, let me give you a helpful tip. Another way to approach this problem, let's simplify the math a little bit. So let's look at helpful tip. A lot of times when you're dealing with distance problems, and a lot of times it has to do with when we're dealing with square roots or radicals. So in order to simplify, work in a distance problem. I mean, we have the tools, we can do this, it's not a big deal, but I want to give you a helpful hint. We can argue the following. Okay, so remember what we were trying to do in the first place. We were trying to maximize our distance. So our d of x wasn't as threatening until we took the derivative. So we have negative 3x squared minus 2x plus 5. Yeah. Okay, so here's the argument. If you already know the expression for d of x, you can obtain the x value that maximizes the distance by finding the x value that maximizes the square of the distance. Okay, so I'll write that down just so that you can kind of say. So we can obtain the x value that maximizes d by finding the x value that maximizes d squared. And you're saying, well, why would I want to do that? Well, it would help if we didn't have to take the derivative of a square root. See all that work we did? Especially when we were trying to figure out when stuff was undefined. So of course we want to get rid of the calculations so that we wouldn't have to worry about square roots. But the reason behind this, just so that you're kind of trying to understand this, the biggest possible value in the radicand is always going to have the biggest possible square root. So In any case, it doesn't matter if you're maximizing d or d squared. We want to care who the x value is. So what we could have done in this problem, we could have just redefined our function. And you don't have to be fancy about it. I just am trying to do this for formal notes. But redefine so that you are looking at your distance squared. And if that is the case, when you square your distance, you are getting rid of the radical. And therefore, you're looking at just a polynomial. So if you're maximizing the square of the distance, you're maximizing f of x, that would say, let's find the first derivative. Well, that's a lot nicer to find. Negative 6x minus 2. Well, guess what? Set that equal to 0. We solved this equation earlier. That's x equals negative 1/3. Now, if you're trying to verify if is it a max or min, this is nicer because you can say, what is the second derivative? It's really quick to take. The second derivative is negative 6 based off of this. And so if you were trying to plug in the critical value or critical x value at the second derivative, there's no x value to plug in. It's still negative 6. It's less than 0. What does that tell you? That tells you your function evaluated at 1/3 is a local max. So what does that tell you then? Well, we had f. So we found the x value that maximized the square of the distance, but now by the same argument, the x value that maxes the square of the distance, maximizes the square of the distance, maximizes the distance itself. So we just saved ourselves a lot of testing to figure out that x equals 1/3 was the answer. So now, my friends, same idea. Once we figured out that x equals 1/3 or negative 1/3 maximizes the distance. When you want to find y, it's the same situation. You're just plugging it into y squared equals 4 minus 4x squared. And we've done that already. I'm not going to spend a lot of time, but you can review that. We still get y equals plus or minus 4 square root of 2/3. And then you've got your points. Therefore, and we've already stated this earlier from our previous version. I always like to finish off the problem so that you guys have something to look at. But wasn't that a lot nicer? So kind of keep that in mind. There's a new trick you just learned to help you. Anytime you're trying to maximize anything that has distance related or something maybe with a square root or radical, it could be just helpful to square everything and then maximize. So hopefully that'll help you out on some of these other problems, even though they're not exactly the same as what we're doing. It does simplify the algebra a lot, calculus as well. So at this point, if this were traditional lecture class, we would take a break and we'd have to refresh our minds. This might be a good time to press pause and see if you really understand what was going on with example 3. Maybe just take a break, refresh your mind. Or fast forward, we're going to go into example 4. And so another idea, again, these are all completely different problems, but they all involve some sort of math from your past to help you out. So let me give you more tricks to use. I don't know if they're tricks, but just strategies. So let's talk. Example 4. A woman at point A on the shore of a circular lake with radius 2 miles. Okay, so what does that mean? Sometimes I see circle, I draw a circle, I do this for you. If they're telling us that the radius is 2 miles. We have to understand radius is the distance from the center to the edge of the circle. And so right now, I'm kind of reminding myself. So the woman, in this case, she's at point A, and she wants to arrive at point C. So she wants to end here. And that's diametrically opposite A on the other side of the lake in the shortest possible amount of time. She can walk at a rate of 4 miles per hour and row a boat at a rate of 2 miles per hour. What is the best strategy to minimize her travel time? So we're assuming everything's constant. And what I'm trying to understand is, yeah, well, if it's a lake, assuming that when she's walking along the arc, well, she'd have to be walking when she's outside here. And she's walking around the lake, she's not going to be able to walk on the water. I know you might say like, oh, the fastest or the shortest distance is from A to C. Well, lady can't walk there. So she's going to have to be rowing when she's in the water. So be careful. So what I want to make sure of, what is the best strategy to minimize her travel time? I have to think. And please don't argue that the calculus needed to decide this is going to take longer than her just walking around or rowing the lake. We want to take our time to decide. So let's see what we can do. Okay, so I'm going to make sure I understand the problem. We kind of set you up with a diagram just so that you can see. She has a choice of rowing, walking, or a combination of both to get from A to C. So if she's going to go straight from A to C, she'd only be able to row because that's the water I'm seeing. If she were going from A to C by walking around, I have an idea that I'm measuring arc length. And there's a couple ways also. She can row from A to B, and then the rest of the way around she can walk from B to C. So we're gonna have to come up with some sort of math to help us out. So let's see what we can do. Everything we know, I'm thinking that I know something about half circles. I'll deal with this in a second. But I really am, what's kind of glaring at me right now is if I were to draw a segment from B to C. I mean, I guess technically she can row this, but what I do know is when I inscribe a triangle in a semicircle, I know this triangle is going to be a right triangle. See, geometry coming back. We haven't used that in a while either. So that could help me out a little bit too. So I'm just kind of piecing everything together. And I also want to be careful. I mean, she doesn't have to row all the way to B. She could have rowed from another point. And yeah, you can still make triangles. But I want to kind of make the point that the distance rowed is going to be dependent on the angle you're taking from point A. So how steep is she going to row? And is she going to row just a certain amount of way, or is she going to row all the way? So let me see if I can make this a little prettier for you. Okay, so let me see. I will mark this angle as theta. Very popular. And a little note. The distance rowed is going to depend on the angle we take from point A. So it depends on what we say theta. Okay, so let's think about what this case would be. She can decide she doesn't want to row at all. So let's kind of come up with situations. So let's talk about rowing 0 miles. Okay, what does that mean? She's walking the whole way. And so what does that mean in terms of your theta? So if she's not rowing, she's walking the whole way. So she's, let's see, she's going over here, from here to here. That means your theta is actually 90 degrees. Okay, so I'll write that in there just so that we have that. And if you want to do 90 degrees, we said calculus and degrees don't get along. So 90 degrees would be pi over 2. Okay. We could think about that. Okay, the other case. If she's going to row 4 miles, that would be rowing all the way. Okay, so she's going to go from here to here. Oh, no. There we go. I'm supposed to highlight, not erase it. So A to C. So she's going from there to rowing 4 miles. That's rowing the whole way. Now, if you're rowing the whole way, you are not rowing your way to the other side of the lake except for your C. So what does that do to your point right here? This is going to now be right here. So this angle that you have, this theta, is not going to exist because you don't have a triangle. You're drawing a straight line. So we have theta equals 0. So kind of some stuff to think about. Let me undo everything. I'm going to erase. Okay. So I'm just trying to understand the situation before I come up with anything. I do know I'm going to have to deal with a triangle, so I could try to play with distances and the angles to help me out. So if we were to look at this triangle, I am going to draw it. Let's see. Let's kind of draw it on the outside so we can help ourselves. Okay, so this is our triangle. I'll have to mark up the picture. I have B, I have C, I have A, I have theta. So a lot of times you're trying to think about distance rowed. You could play around. We already know that this side is 4 miles based on our picture. We don't know the distance from B to C, but we do know from A to B would be kind of where she's talking about rowing. So I'm just kind of piecing together possibilities. Okay, so I'm just thinking, what can I know with the triangle? I know that I can relate the distance x with the 4 by taking the cosine of theta. So cosine of theta is adjacent over hypotenuse. In this case, the hypotenuse is 4 miles. You got to be careful, it's upside down. If you want to flip it around the way you like, it's okay. So that also could tell me that I already know the distance rowed. We can set it up with x equals 4 cosine theta. So I have something to help me. So that could help me with rowing. But I also want to talk about distance walked. Remember we were talking about rowing has to do with sort of a triangle, walking has to do with arc length. So before I even go there, let's talk about y. And I'll try to piece this all together. So y is going to equal the distance walked. Now we're reviewing. Okay. Now recall, we have geometry coming back again. In geometry, we have arc length. And remember, if you had, I'll draw my best circle that I can. We talk about when you have an angle a triangle or some sort of, how do you say, a point on the circle, and you're drawing two chords in the circle. There's a couple of relationships from our past. If we're calling this angle theta, the measurement of the arc length is 2 theta. That's something I probably wouldn't have come up on my own unless I really studied my geometry. We don't use that too often, but this problem is going to be necessary. Okay, so we know that relationship. And we also know arc length. There is a formula for arc length. Also, arc length S equals r theta. So in our case, we know it's 2 times theta based on what we know the relationship between an angle made by 2 chords. Fun. Okay, so I'm kind of piecing all that together. And I know that the woman is not going to walk completely around the circle. At most, she can walk halfway around. So I do know that when she walks, it's a fraction of the circle. Okay, and if we're talking about the circle, I want to be a little bit more precise. If I'm speaking about all the way around, distance around circle, it's a fraction of the circumference. Well, these things you have to be patient with. So let's talk. I can now relate this. Okay, so the circumference of the circle. Okay, circumference is pi times diameter. In our case, our diameter is 4 miles. So we should have pi times 4, which is 4 pi. So when you talk about the distance walked being a fraction of the circumference, the first thing I need to do is figure out what the fraction is. But I do know the circumference is 4 pi. Okay, so what fraction of the circumference? So just remember, we're looking at our picture one more time. We're looking at the distance walked. It's going to be, in some case, 2 theta. Part of the whole. That's what fractions are. Part of the whole. So 2 theta, I'll make theta nicer. And the whole circle would be 2 pi. That's a lot. So she walked the whole way around, 2 pi over 2 pi, one circle. Well, now we can simplify. We have y equals, that the pi's divide out, 2 goes into 4. So we have y equals 4 pi. I say pi, I meant theta, excuse me. See how the pi's divide out? Here we go. Okay, so we're going to get back to this. Distance walked. It's in terms of an angle this time. Okay, so I'm going to piece this all together. There's a relationship between rate, time, and distance that we also have to bring into the problem. Remember how they also said that she's walking at a rate of 4 miles per hour and rowing at a rate of 2 miles per hour. Let's try to bring this into play. The relationship, rate, time, and distance. Guys, remember that formula? Whew. Rate times time equals distance. And so a lot of times you guys like to see this R times T equals D. So we can play with time because what are we supposed to do in the first place? We're supposed to minimize travel time. Okay, let's go with it. Let's talk about the time rowing and the time walking. So the time rowing, I'll use subscripts. Okay, so what we can do is take this rate times time equals distance, solve it for t. What is that? T equals d over r. So if I kind of make this in terms of our problem, the time rowing is the distance rowing over the rate rowing. Well, what do we know? The distance we're rowing. Okay, go back. Remember, we're talking about the distance rowing. We relate it to a right triangle in terms of cosine theta, but then we solve for x, we have 4 cosine theta. You could do that. We got it. 4 cosine theta. Now the rate rowing, they already told us, it's what, 2 miles per hour. Now, if you want to simplify this a little bit, we don't need a complex fraction. We should have 4 over 2, that's 2, no problem. Now, if you have 4 cosine theta, let me make sure we're talking about miles. So we also have miles on top, divide out. So we have 1 over hour in the denominator. That's what this means, 1 over hour. So if you have a reciprocal, 1 over hour just means hours over here. And let's make this, I need to put the cosine theta in there. Sorry about that. So we actually have a time now, 2 cosine theta hours. Okay, we're almost there. We're getting there. Let's also talk about the time walking. Okay, so you're probably saying, okay, that's the distance walked over the rate walked. Well, we know the rate walked is 4 miles per hour. And then when I want to talk about the distance walked, we just kind of worked through that it's an arc length and it's 4 theta. That's this piece right here. And if it's a distance, remember it's in miles, and the same reasoning, if we were to simplify, all we have is theta hours now. Okay, so we are almost there. We're trying to come up with her travel time. Okay, so travel time, one more time. Travel time is the time rowed and the timed walk. So that can be written as t in terms of theta. So the time row, we came with 2 cosine theta, and the timed walk actually happens to be just theta. And what we want to do is we need to minimize. And we're saying why? Well, I'll go back, read. Minimize the travel time. And we also decided, kind of looking at what were the possibilities for this woman. She can walk the whole way, so that's theta equals pi over 2. Or she could row the whole way as well. That's kind of the 2 extremes. So what we're doing is we're minimizing on the time interval, or the theta interval, 0 to pi over 2. So we want to take care of the 2 extremes and what could happen where she takes a combination of rowing and walking. So that is a lot to kind of pull back from geometry, trig, and then also a little algebra with rate times time equals distance. That is quite a bit, my friends. But once we do have this equation, it's not as complicated to actually the calculus on. So again, if you're trying to minimize, what we want to do is, let's see if we could take the first derivative. Well, that's a nice one to take the derivative with. The derivative of cosine is negative sine theta. And the derivative of 1 theta is 1. Make it a little prettier, negative 2 sine theta plus 1. And we're trying to find critical points. We're going to set it equal to 0. Not theta, 0. So if we do that, we get 1 equals, add 2 sine theta to both sides. Or we get 1/2 equals sine of theta, or if you like to see it the other way around, sine of theta equals 1/2, and we know theta for this. That gives us theta equals pi over 6. That's where the sine is 1/2. So now, what do we have to do? We need to verify what this means. Verify if this is a max or min. We can't just assume. So when I'm looking at my first derivative, it's not too complicated, so I can use the second derivative test. Let's find that second derivative. If I take the derivative of sine, I get cosine. There should be -2 cosine theta. Now if I plug in my critical point, that's -2 cosine pi over 6. What is that? Well, cosine of pi over 6, if you're thinking about, you don't even really have to come up with a number. Cosine of pi over 6 is in the first quadrant, so it's positive. But negative times positive gives us negative. So if it's a negative number, that's something that's less than 0. So we do have a local max. Okay, so that's what's happening at pi over 6. But what were we supposed to do? I know, don't get too excited, because what do we want to do in the first place? We wanted to minimize travel time. We don't want to maximize travel time. So this is what we mean about checking. If you don't check, you would not know that this is not what we need. We want to minimize. If you were to stop here and assume that that was the critical value that helped, then you would be wrong. So then we have to think. Now this is like an in-depth problem. Well, if our critical number gave us a max, we don't want to maximize time. I guess if she was trying to avoid something on the other side, but most of the time people want to get a short amount of time in. What's the other possibilities? Where are the extremes of the functions? So other options. Okay, here we go. So other options. If our extreme values are not occurring at the local min or local max, we go back to speaking about absolutes. And again, we're looking for, the only case would be if we had an absolute min. And they occur, remember absolutes, they could occur at your critical points. Or the endpoints of the interval. That's really pulling in some calculus we haven't had to deal with in a while. I mean, this is kind of at the beginning of the chapter. So right away, it didn't work for us for the critical point. We got a max. So we're looking for the min. So we're going to look at the endpoints of the interval. We're going to check this. So what we need to do is we need to evaluate t of theta at the endpoints. This is why we had to think through this so much. And the endpoints of the interval are 0 and pi over 2. Remember we spoke about her extreme in terms of she could walk the whole way or row the whole way, and there's no other possibility. So just kind of reminding us that t of theta is 2 cosine theta plus theta. The endpoints would be t of 0. So 2 cosine 0 plus 0. And so what is 2 cosine 0? Got it. I always write my zeros and my thetas. Cosine of 0 is 1. So t of 0 is 2 hours. This would be if the woman rode the whole way. You really have to understand your setup and trying to see. Oh yeah, if theta is 0, it's non-existent. She's now just rowing across the lake. Okay, 2 hours, not too bad. We already could have figured that out, by the way, because if she rows 2 miles per hour and it's 4 miles across, then yeah. We didn't really need trig for that. But we do need trig to talk about what's happening at the other value. So we'll be looking at t of pi over 2. So what is that? 2 cosine pi over 2 plus pi over 2. And remember at pi over 2, cosine pi over 2 is 0. So we have 2 times 0 plus pi over 2. So that's pi over 2 hours. So who thinks like that? You probably want to approximate that. Pi over 2. Is that 1.57, 1.6? And that's her walking the whole way. So my friends, you could also think about, well, what is t of pi over 6? Just in case you're wondering, we'll note. To further verify this, you know, sometimes you don't always want to believe me. If you say 2 times cosine pi over 6 plus pi over 6, we end up getting about, I'm going to save you some time, 2.3 hours. That would be her rowing at an angle of pi over 6 from the horizontal and then walking the rest of the way. So rowing at angle 30 degrees, that's pi over 6, then walking the rest of the way. Can we point out when we're looking at these two values, I'm going to shrink it down a little bit. We have 2 hours, we have 1.6 hours, we have 2.3 hours. Well, who's the smallest of them all? 1.6 hours. So that, my friends, that is the absolute min. So what should the woman do? Therefore, we're going to end this up. Therefore, she should walk the entire way to minimize her travel time. And that is us stating the result so that we're relating English to all the math we just did. And I know that seems like a pretty intense problem. And you really have to kind of have an understanding of trig. But I also like to point out that calculus did not take us longer than 1.6 hours. So it's worth her time to kind of sit through this. So something to think about. Again, if this comes up, we're kind of playing around with how do we relate triangles into the problem. And then we had to think about, oh yeah, formulas from our past, rate times time equals distance. And then trying to really understand that the moral of the story is sometimes, see if I can find this for you guys. Sometimes when you find a critical number, it's not always what you need. This is kind of what I want to point out. So thanks for sitting through that. And again, this would be a great time to take a break, but I'm gonna go forward because you guys can press pause if you need to. But I have about 3 more examples. I don't believe they're as complicated. Maybe this other one's a little, I'll give you 2 versions on how to look at example 5 as well. Sometimes when you have X coordinates and Y coordinates, sometimes that tends to give you a couple of different options. So let's bear with me. So that's 3 examples. And remember, my whole point of this section is to show you enough so that you can kind of use some of these tricks to help you out if you end up seeing problems that you're not familiar with. So here's some more strategies. Now what we are looking at, we are trying to find the area of the largest rectangle that can be inscribed in a semicircle of radius r. And so I really want to understand what I'm talking about. So semicircle, that is a half circle. What to kind of think about. Let me draw a sketch, let the gears in my brain move a little bit. Here's my semicircle, the best one I can do. and they want the area of the largest rectangle. So I know I should have probably made a better one. I'll do my best. So let's say you could draw your rectangle a little taller. You're inscribing it, right? So you could look at that area. Or we could think about making it a little wider. But if you make it a little wider, it becomes a little shorter. Or if you make it really wide, it becomes really short. So there's a lot of different options that we have going on. But like it's really hard to tell just by eyeing it. You kind of have a guess of what kind of looks like a larger angle, but sometimes it could be tricky. Sometimes the long and skinny rectangles kind of look like they might have larger areas than we think. So there's many possibilities, again, kind of like what we were doing with that ellipse when we're trying to find furthest distance. And I also want to point out, there are a couple things. They gave us radius r. So remember, if you're thinking about this, that's the distance from the center to the edge of the circle. And it could be anywhere. It doesn't have to be on a straight line. You can kind of draw it from wherever perspective, whatever works best for you. But if they're asking us for the area of the largest rectangle, the answer is not going to be a nice number because it gave us just r. It might give us a number next time, but let's come up with it. So if you're interested, and maybe you're tired of hearing my voice, I do know that kind of convenient example 5 in our textbook. That's on pages 262 of the textbook. Could help us out with something similar to this. So feel free to read through this if you're tired of hearing me. I know it's a longer lecture today, but I'll show you my spin. And then if you like that, fine. If not, there's always other options. But a lot of times if I'm trying to really relate area, largest rectangle, the best way I can do if I don't have nice numbers is I will try to relate things with X and Y. And sometimes by imposing or superimposing your semicircle on an axis or coordinate system, this could help. So I'm going to see if that works for me. Here's my coordinate system. We love coordinate system. We're going to draw our semicircle the best we can, or the best I can, I guess. And remember, the idea is to inscribe a rectangle. So what that would look like, and it doesn't matter how I do it, I'm just trying to get an idea. I'll just draw one sample rectangle. I have a sample rectangle right here. And so now if I'm on a coordinate system, I can now talk about the radius. We have a couple ways. Radius can be the distance from the center to a point on the circle. So we know that that's r completely. But that doesn't help us if we don't know what the values are. So I might be a little bit more liberal with this, and maybe the radius, we're going to draw it at a diagonal, and it would be convenient to put it like on the corner of the rectangle. Kind of nice. So that's also r as well. And when we do that, we end up relating r with a x and y value. And even better, my friends, when you do that, you have relationships. When you have a circle, what do we have? If we relate r with x and y, we have the equation of a circle centered at the origin. Check it out. X squared plus y squared equals r squared. And I don't know if this is going to help me. Personally, like what I do is I try to come up with relationships and see where I can use them. I do know that they're talking about circles, and I know equations of circles help. But I also want to deal with the fact that they wanted me to find the area of the largest rectangle. So when I'm really goal-wise, I'm supposed to be, I know, little note to myself, I'm supposed to be maximizing the area. And I know with area, area is always equal to length times width. So if I'm trying to understand this, I'm like, well, the way I've superimposed my circle on a coordinate system, I actually can relate my distances a little bit. So for instance, again, remember if that coordinate that we just chose right here, that point is x comma y, it means the horizontal distance from here to here is x. And the vertical distance from here to here is y. So that's kind of nice. That actually tells me a little bit more. What does that mean? I know how rectangles work. I know that the opposite sides are equal. I do know if it's the semicircle, if I centered it correctly around the origin, I do know that there's symmetry going on. So I can guess that there's a distance from here to here would be x. And then that also tells me if everyone is x, then I have x here and I have x here all together. That makes a 2x. So what I've just done is I've taken a rectangle and I now know the length and the width in terms of x and y. So that's kind of nice. You could do it in L and W if you wanted, but we had to kind of make it related to the circle somehow. So the way I'm seeing it with my circle, my length is 2x and my width is y. And if we're kind of going through this, we're saying, what does that mean? Make it pretty. Area is 2xy. And the issue is this. Remember how whenever you're trying to maximize something, the idea is we need in terms of one variable only, in a sense. So that's the idea. If we don't have that, we have a little trouble. Because remember, we are single variable calculus. So this is what I also want to show you. You want to maximize this expression, 2xy. Here is another trick you could use. Remember on the same idea, if we were looking back, a lot of times when things are related to coordinate systems, remember back here, that if we wanted to maximize just the single distance, it involved the square root, and we didn't want to deal with the square root, so we could say, what if we tried to maximize the square of it? And you're like, yeah, we can do that because we get rid of the square root. Well, what does this mean in terms of our problem? Scrolling, 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 here we go. Well, this is all I know. Remember how I said we tried to relate it to the circle? And when I'm looking at, the only thing I know that relates x and y to a circle is the equation x squared plus y squared equals r squared. So I'd be able to do some substitution if I can introduce an x squared or a y squared. But I can't just introduce for the heck of it. I have to have a reason. So my trick, if I want to maximize, my trick is to try to maximize the area squared. You'll see why in a second. Could help. What does the area looking like? Well, we had started off at 2xy. But if I'm trying to maximize the square of it, it's going to maximize the area in the general idea. Well, let's make this a little prettier. When we square 2xy, we get 4x squared y squared. Well, I mean, this is really exciting. Now it's a lot easier to introduce our equation. It's much easier to substitute in, what is it, x squared, well, let's make it prettier, relationship between x and y, x squared plus y squared equals r squared. And depending on what you want to work with, you want to either turn it all in terms of x's or all in terms of y's. And so, I don't know, I'm just picking this one, the y this time. And I know y squared is r squared minus x squared. So it's a lot easier to do this. And I bet you're probably thinking, wait a second, you just made it look uglier. How come you still have two variables? You have x squared and you have r squared. But I have to note for you, r squared is technically not a variable, it's a constant. It's not changing. The circle is remaining the same. So technically, we did not make it harder. Everything is in terms of x squared. Depending on what r is, it's going to be a number. So just kind of keep that in mind. R squared or r, they're constants. So when you start taking derivatives, you are not dealing with anything to do with the r's. They just get treated like numbers. It is not implicit differentiation. You kind of know when the radius is changing. They have to tell you. Remember, it wasn't. So finally, what we just did is we were looking at area. And yeah, I mean, you can call area A, but if you're talking about the area squared, it's not really A anymore. You can rename it any function you want except for A. Don't spend your time being confused. So I just go, let's name it F, and it's in terms of what variable? Not R. R is a constant, it's f of x. So there is the equation that we have in mind. We really want to maximize this one, because we're maximizing the area. All right. Now, this is not too bad. Let's make it a little prettier. I know, like, if ever I want to maximize stuff, it's really helpful to not have function times function. So if I have a choice and I can distribute, I will. I should have 4x squared r squared minus 4x squared times x squared x to the fourth. So that's a little nicer. But now we can take the first derivative. And remember, r squared is constant. So if you're trying to take the derivative of 4x squared r squared, 4r squared is already constant, the derivative of x squared is 2x. And so the derivative, the other term, it's in terms of x, the derivative would be 16x to the third with a negative. Let me clean this up a little bit. That will be 8r squared x minus 16x to the third. And if it's, I don't know what works better for you. Let me make it prettier. I know that 8 was a little ugly. Okay. So again, this is the part we were looking for. Do we want to find our critical number? We do. So remember, critical number, it's a polynomial. We're going to set it equal to 0. See what we can find here. You know, when we set it equal to 0, it is factorable. There is an x in each of these problems. I will factor. In fact, I'll take an 8x out. Make the numbers a little prettier. So if I take an 8x out, I have r squared minus 2x squared. Remember, r is a constant. So I have a factored polynomial. I have an idea. If I solve this equation, I have 8x equals 0, or r squared minus 2x squared equals 0. Well, this equation, x equals 0. And if I solve the other one, what should I say? R squared equals positive 2x squared. But if I'm solving for x, divide by 2 divided by 2, x squared equals r squared over 2. And then if you take the square, well, let's try to make it prettier for you. If you take the square root of both sides, remember how, because we're speaking that we're only going to get positive cases if we're talking about distances, we get absolute value of x. So I think that's going to be r over square root of 2. And so that's going to be another option for x. You can even just say x, because what do we care about? We care about the positive case. I know normally you're like, oh, it's plus or minus, but remember, we're looking at a distance, r. So you can kind of just say, okay, that's the same thing. R over square root of 2. If you feel like rationalizing, have fun. Now, just kind of remember a note. R always positive. You can't see that, huh? These are quite complicated, but you have the brain power to get through these. It's just that we have to do a lot of them to be confident with taking a step in the dark, as we said. So let me go back and say, what was I trying to deal with? I'm looking at x equals 0 or x equals r over square root of 2. A lot of times they care about what they say is feasible domain. When you look at what is your x related to, well, we made this picture over here. And x has something to do with the length of a side of a rectangle. And what happens if x is 0? If x is 0, you get 2 times 0. You can't have a rectangle that has a side of 0. So we throw this out of our domain. It's not in the feasible domain because there's no rectangle if you don't have a side. So if you think about it, you don't have to work as hard if you understand the context to the problem. So now we have good news. Okay, we have one possibility for x. It could be a max, it could be a min, it could be neither. So what we're looking at is we need to verify. We must verify. Remember how it didn't work for us the last time. So we must verify if we have a max. Okay, so we have the choice, first derivative test, second derivative test. And what I'm looking at, if I see my first derivative, I'll highlight it so we see. A first derivative is a polynomial, so I'll kind of write it down so we can have that. That's 8r squared x minus 16x cubed. This is not too hard for us to take a second derivative. We like polynomials. So if we were to take a second derivative, what am I looking at? And then this is where we have to be careful, is because 8r squared is a constant, so there's no derivative on r's. So it's like taking the derivative of 5x is 5, right? The coefficient. And the derivative of 16x cubed be 3 times 16, I think. I know my brain's been through a lot today, so let's do the calculator to make sure. 48. That's 48x squared. And so what I want to look for is I want to plug in critical value or to see. So I'm looking at r over square root of 2. And I'm trying to determine, am I getting a positive or negative number? Well, I have 8 something squared minus 48. Sorry, let me do this one more time. Okay, remember, f of x. So you have to catch myself. We're plugging in for x, not r. Tricky. So you have r squared. That's still r squared, still a number. It's the 48x squared. That is r over square root of 2. Let's clean it up just a little bit to interpret. I have 8r squared minus 48r squared over square root of 2 times square root of 2 is 2. Want to make it a little prettier? 8r squared minus 24r squared. Want to make it prettier? Take out the r squared. R. I guess you could have combined like terms too. That's the same thing. So we have negative 16r squared. Okay, so then you have to decide. Well, we don't know what r is, but we know r is always positive. So r squared has to be always positive. So what does that tell you? Negative times positive, that's going to equal negative. And negative means less than 0. So my friends, what does that tell us about the function evaluated at r over square root of 2? Remember, if the second derivative is negative at that point, that means you have a local max. So now we're confident. Yes. So r over square root of 2, whatever that circle happens to be, that's going to tell us information about the x and y value. Do we even need that? Let's find out. The area of the largest rectangle. So let's go back to area. And remember, okay, so I'm gonna piece this together. So remember, the whole idea is we need to answer the problem. Okay, so now answer problem. I know sometimes you get so excited that you find something and then you stop, but there's more to this. Okay, so we need to find the maximum area. So remember, maximum area, we actually found the area squared in our formula. Okay, so let's kind of keep this in mind. F of x, which is equal to, what is that? 4x squared r squared minus 4x to the fourth. That, my friends, is equal to the area squared. I have to kind of be careful about this. That was our trick so that we could relate our x's and y's. So keeping that in mind, yes, we can still substitute in, what was our favorite value we found? R over square root of 2. Okay. I'll widen that out for you. So r over square root of 2. Again, you're substituting in for x. I guess if you wanted to factor, you could have, but we'll go with it. So we have 4 times something squared times r squared minus 4 times something to the fourth. Again, it's r over square root of 2 that we're plugging in, keeping in mind that we're taking those to powers. Okay, so clean it up, take your time. This is not time to go fast. We have r squared with another r squared, and square root of 2 squared is just a 2. We have r to the fourth, and now square root of 2 to the fourth. Square root of 2 times square root of 2 times square root of 2 times square root of 2. 4 of those is a 4. Clean it up. 2r to the fourth minus r to the fourth gives you r to the fourth. So that is the maximum area squared. Keep in mind, it was a squared equals r to the fourth. So a, what happens? Take the square root of both sides, you should get r squared. Interesting. So the maximum area is actually r squared. It came out so beautiful. Look at all that math. Wow, we did all of that for r squared. So now you actually have a formula if you kind of were checking yourself. No matter what you know what the radius r is supposed to be, if you're ever going to inscribe it in a semicircle, the maximum area depends, it's definitely related on whatever the r happens to be. Probably knew that already, but I didn't know it was so pretty, r squared versus r. Okay, so this is one way to go. And knowing what you know, a lot of people like taking derivatives of polynomials. And it doesn't hurt. We don't need any tricks. We have one trick where we have to square the area to help us introduce We didn't know how to solve for x and y. So I mean, that could work. I'll give you another option. If you are trig-minded or you were needing a break from x's and y's, maybe another possibility another possible route to take your solution from. You could, and this is up to you. You don't have, I don't have a preference. I just want to show you options so that you can pull from them when you need them. So I've got my rectangle inscribed in my circle. And again, we realized that when we did this, we defined it so that the R would be the distance from the center to the outside of the circle. And then we had a point. And then we kind of thought through it and we know we had X and Y. And then what you could do, now, this is up to you depending on what you like better. We could redefine X and Y in terms of theta and R. And why? Why would we do that? Well, X and Y make legs of a right triangle. We can then relate it to trig. And that's kind of a big thing in calculus. Calculus 2 uses a lot of trig. So I'm just trying to keep that fresh in your mind. So what does that mean? If you're trying to do this, we're trying to talk X and Y, right? X and Y, remember that kind of has to do with polar coordinates, but you could also go the other way if you want to talk about X equals or let's even do it so that you see it. Theta, right? Cosine of theta is X over R, so that could solve us for X. X equals R cosine theta, so nice polar equations. And the same thing with sine of theta. Sine of theta is Y over R. According to our setup, if you switch X's and Y's around, you'll have a little bit different. But as long as you're being consistent, you should be okay. And you're like, why would I even want to do this? If I feel confident with the other part, like I said, I'm just giving you options, but I also want to keep the trig in your mind. Eventually, a lot of you are going to move on to calculus 3. And sometimes it's easier to take everything from X and Y, rectangular coordinates, and convert everything into polar. Makes integrating easier, whatever that means. Well, we'll get there. So I just want to have the trig fresh in your mind throughout the entire calculus series. Now remember, we already talked about how if you're talking about the area of a rectangle, it's length times width. So we had this area is length times width, and length times width in our case was 2x times y. So if we were, I'll make it prettier for you, to redefine everything, instead of x, we would write it in terms of r cosine theta. And instead of y, we would write it in r sine of theta. So at this point, remember r being a constant, you now have the area in terms of only one variable theta. So let's clean it up. That's 2r squared cosine theta sine theta. And now I'm going to flex my trig muscles a little bit. And I'm remembering, we rearrange it right there. You see this a little bit? You remember trig identity? That is equal to sine of 2 theta. So I not only was able to convert area in terms of just one variable, I can convert this equation in terms of just one trig function. So trig identity, 2 cosine theta sine theta is sine of 2 theta. A little nicer if you have to ever solve equations. So what do we have? R squared sine of 2 theta is area in terms of theta. And so if you're comfortable with that, then sometimes the derivative, not too scary at this point. Now, you know, we're trying to find this critical value. You can say, all right, well, let's look at the derivative. R squared is constant. When you take the derivative of sine, you should get cosine. But remember, we're looking at the chain rule. Let me make sure that theta looks like a theta. And that we'd have to multiply that by 2. So that could be a tie-in. So I have 2r squared cosine 2 theta. And now I can take this, if I'm looking for a critical point, I can take this and set it equal to not theta, 0. And what does that mean? Well, remember, 2 and r squared, they are constant. They divide out. So we get cosine of 2 theta equals 0. And so this is a trig function with an argument more complicated than just the theta. But we do know the cosine is 0 at 2 points on the function, or 2 angle measurements. The cosine is 0. Draw a little quick little idea. The cosine is 0 at pi over 2 and 3 pi over 2. Remember, you're looking at what? 0, -1, and 0, 1. Sometimes we don't think about that, but we have 2 possible values in the 0 to 2 pi. But when you solve for theta, what are you dividing everything by 2? So you should have theta equals pi over 4 or 3 pi over 4. Now, what I probably can do if I am considering the picture and the idea of what I'm looking for, I can test both of them and see what works better. But look at this again. The way you've defined everything, when you're inspecting possibilities for theta, it seems like there's going to be a max if you've redefined everything in terms of x and y. If your theta is bigger than pi over 2, we don't have to consider this. We're not having a rectangle anymore. We'll have an issue. So I'm just looking, by understanding the context of the problem, I'm trying to eliminate some of my work. Feel free to play and see what happens, but there's no realistic idea of keeping 3 pi over 4. So the last thing I have to do is verify. Okay, and so I need to verify if a max. And so remember what I need to do. I'm going to trade off. I have, I'm going to rewrite my trig function. Sometimes my eyes will skip, so I have to be very careful. So I have my first derivative was equal to 2r squared cosine 2 theta. So if I want to take my second derivative, okay, so 2r squared is a constant. If you want to take the derivative of cosine, it is negative sine of 2 theta, but the chain rule multiplies it by 2. So let's clean that up. That's going to give us a negative. I should put that, maybe color it in. That's a negative 4r squared sine of 2 theta. Okay, well, let's test it. We need to plug in second derivative test. We're going to plug in pi over 4. So if we do that, I'm just being real patient, I know. We have sine of 2 times pi over 4. And you want to make it a little prettier, I'm going to move sideways so I don't run into the next example. So we have negative 4r squared. Now sine of 2 pi over 4 is the same thing as 2 pi over 4 is pi over 2. and sine of pi over 2, that is equal to a 1. So we don't have to worry about that. And now, let's think about this again. R squared is always positive. The -4 is negative. So negative times positive equals negative. That's a less than 0. So what does that tell us? If the second derivative is evaluated at the critical point is 0, then you've got yourself a local max. The area evaluated at pi over 4 is a local max. Yay! So are we done? No. No. One last thing. What were we trying to find in the first place? We needed to find the area. So the last thing I want to do is actually go back to where I was. So we may need a little bit more paper. So answer the problem. I'll go over here for you guys. And this is why they kind of go over problem solving a lot in algebra classes. It's not always about getting the answer. It's actually, did you answer what the problem was asking for, and does everything make sense? So remember, I wanted to maximize the area. So what was the area in terms of theta? Go back just so that we can see it. It was r squared sine of 2 theta. Sometimes like rewriting what the actual equation was instead of skipping your eyes over, so it kind of minimizes mistakes. So we are looking at plugging in pi over 4. So we get r squared sine of 2 times pi over 4. And we get r squared sine 2 pi over 4 is pi over 2. And sine of pi over 2 is 1, so we get r squared. And so that should look like an r squared. Therefore, from our work, the maximum area is r squared. And if you compare your work to the other problem that we just did, or the other version, we got the same answers. So what are we trying to say? Does it matter which way you do it? No. Whatever works best for you in Calc 1. Personally, it looks like the same amount of writing when I look at it, and I guess it would be something. I guess it's a little nicer because you're not having to worry about the square of the area, but you also have to know a little bit more trig to get through it. So it's always a balance, you know, the lesser of the two evils. But we did get the same answer, so I think that's really cool. So good practicing on that. Again, what's the benefits of exercising this if we don't really, if we feel like maybe the other solution that we did up here was nicer? I'm just trying to prep you for, sometimes you do want to write things in terms of theta. It'll help us later in our next classes in the calculus series. Take a break, of course. I'm going to keep going through. You can press pause. Sometimes you need to get up and stretch. We have 2 more examples to go over. And I feel that they're not as intense with trig-wise. I see a lot of these more in a business calculus class, but I'd like to also, you know, a lot of you are dealing with analytical geometry here, but you know, there is some application too to some of these business models. So I'm going to do 2 more examples to hopefully give you all the tools you need to tackle these problems in the section. So again, I do realize if you need to take a break, that's fine, but I will keep moving forward. Example 6, we have a manufacturer determines the cost of making X units of a certain commodity is given by the C of X function. And they also gave us the demand function. And I'm noticing right away the C of X got some decimals, but it is a polynomial, as is P of X. So 2 parts. We define the production level that maximizes profits. And we also have to find the production level that minimizes average cost. So we're optimizing in two different situations. So first off, we have relationships that we know from business models. We've dealt with costs before. And what we'd like to do for ourselves, if this will let me write, oh, there we go. It's getting a little tired, I know. Okay, so part A. One thing I'm noticing is the word profit. So what we need to do is, what's the relationship between profit and cost? We have profit equals revenue minus cost. And we do know what the cost function is. It's given to us. We do need to deal with the revenue function. And a little bit of experience from some of the other problems we've done, maybe, or even if you don't have experience, it's okay. Revenue is given by multiplying the units you produce by your demand function. So our demand function is P. So just kind of think about it. If you're trying to sell items at $2 a piece, however many items you sell, you're multiplying it by I'll just say the demand. And if the demand in this case, they sell at $2 a piece, multiply number of units times your function. Sometimes it's not as easy as just multiplying it by the price you plan on selling it. The price always depends on how much you're producing and what the demand is, hence the P of X function. So let's plug this in. We have X, and then P this time is 48.2 minus 0.03X. So clean it up a little bit. Looks like a distribution, 48.2x minus 0.03x squared. Well, now if profit is revenue minus cost, what we'll be looking at takes a little longer. We have the 48.2x minus 0.03x squared. We're going to subtract off our cost function. And because cost function is more than one term, we have to use parentheses. So what do I have? I'll write it down. And yeah, we could do a lot of mental math at this stage because sometimes our hand, I mean, especially after going through this, is tired. But I encourage you to write your steps out because one little mistake throws off the entire function. 1800 plus 25x minus 0.2x squared plus 0.001x cubed. Okay, so again, this is profit. And what we're looking at is you're probably going to want to maximize profit, so it's probably going to involve taking a derivative. What I would assume is we probably want to clean it up before we even try to take a derivative. So what you see me distributing the negative sign. That's usually the mistake everyone makes, is forgetting that. So I should have negative 1800 minus 25x plus 0.2, I'm going to color code that for you, 0.2x squared. And again, it'd be minus 0.001x cubed. Okay, maybe you wanted to vertically align these up. It could have been a little nicer. So again, this is all profit still. I haven't done anything with derivatives. Now it's just a matter of combining like terms. And while I'm here, I'll just write it in descending order. Makes our lives a little easier. So I don't have any cubes other than 0.001x cubed. So I'll write that first. Then I'll look at combining any x squared terms. So I have 0.2x squared minus 0.03. So it's going to give me 0.17 positive. Be careful if you forget where the decimals are located. That could throw us off too. Now I'm going to look at the x terms. 48.2. I'm subtracting off of 25. So that should give me 23.2 positive, but with an x. And then I still had negative 1800. Okay, so we have profit. It's a cubic polynomial. And again, if you want to maximize profit, the next thing you're probably going to do is take the derivative. Let's find p prime x. And if you take the derivative, well, we have negative 0.003 x squared plus 2 times 0.17. Just want to make sure, 0.34 x, and then plus 23.2. Get rid of 1800 is 0. So what's going to happen is we're going to set this equal to 0. And there are ways to do this by hand. I'm not that excited about it, to be honest. So this is where we're going to pull our technology into play. I'm sure if you multiplied everything by 1,000, you can get rid of the decimals. And it might be factorable. But if it's not factorable, it is still a quadratic equation. You could also use the quadratic formula to solve. And that's perfectly fine. But if I have the use of my TI, I'm doing it. I'm going to go with that way. So I'm going to take my TI. And I'm going to see, I know it's a parabola. I know it's going to be facing downwards based on the behavior. But what I care about are the roots. What are the x values that are giving me this equal to 0? So let's go to our TI. Probably saves me a little bit of time. So remember, I'm looking for where my first derivative is equal to 0. I could plug in my profit if I want to be clear about this. But what did they ask me for? Find the production level. So that's x. Okay. Like I said, I'm thinking through things. But first of all, let's plug in your derivative. So negative 0.003 x squared. Always just being careful. One extra 0, it does throw it off. Plus 0.34 x plus 23.2. And just double check. Is everything plugged in correctly? Got my signs, got my decimal points. Okay. I think if I press graph, I've got, I'm off the grid a little bit because of my ideas of the function. So you can play around with the window. A lot of times what I do, I know I'm not in the standard 10 by 10. Sometimes you'll see me cheat a little bit and go down to zoom fit. It's not the best way. Sometimes I can tell by what my y-intercept is, but I'll show you guys tricks while we're here. So it kind of gives us an idea. We knew what it was supposed to be. It's supposed to be a parabola that's facing downwards. It appears that the vertex is going to be somewhere on the right of the 0. And now I can adjust my window a little bit better. See what it gave me. It zoomed me. My x mins and my x max, my y mins and y max. Yeah, I could have probably figured that out. But let's make it a little bit, I want to see the entire one just so I can tell you what I'm looking for. And let's go maybe, let's do negative 50 and positive 50 for x's. See where that lands us. And I also want to go a little bit higher because I remember it didn't really hit. So let's keep our y min the same and let's just make our y max 50. Sometimes I just want to be square and see what I got. Okay, I'm getting a better idea. I need to move over a little bit for my x max because the right side of the screen has to grow. So let's double it. You can always change your mind and go backwards. And maybe y min, I just want to see the bottom a little bit. Let's just make it a little symmetric with y max. Let's see what happens. Oh, still. It's like those X mins and my X maxes. Okay, I just want to see all of it. Let's grow it bigger. Let's go negative 200 to positive 200. And I know you can find this without, but I just want you to see this parabola. So it's kind of what we thought. Again, this is the derivative, and you want to find where the derivative is 0. So there's 2 points. There's the point where it's to the left of the origin, and then there's a point where it's to the right of the origin. And what makes sense with production level? Can you produce negative X units? And what do you think, Leica? Nope, you can't. Okay. So if you are looking at the graph, you only want to spend time calculating the right side. So I'm going to calculate the 0. And I have left bound, right bound. And that's where the derivative is 0. Like I said, we don't care about the negative value because it doesn't make sense with the context of our problem. So we got something like 161.28. So I'll just draw a picture so you all see. Just a quick sketch. You could have done this with quadratic formula. I don't know if it takes you longer to find a window or longer for you to plug in formulas. But let's do this. So just a quick sketch of my reasoning of what I was trying to think of. I'm sketching the first derivative, that's p prime. And I cared about whatever this point was. And we figured out that that point was equal to 0 when our production level was equal to about 161.3. Well, if you think about production level, can you produce 0.3 of a unit? Probably not. So you could probably say about 162. People don't really like to do point, but we're trying to be precise sometimes. Now, what you could do when you're looking at the 161.3, you can use this derivative to tell you when your derivative is positive or negative. So, I mean, yes, you could take the second derivative and plug in 161.3 and see what's happening. But since we already took time to make a graph, what you can do is just look on the left side of 161.3 for most of this. You have the p prime being a positive y value. And on the right side, the p prime is negative. See how you have values above the x-axis and values below the x-axis, positive, negative. So what that gives you information about is your p. If your first derivative is negative, your p is decreasing on the right side of 161.3. And if your first derivative is positive, your p is increasing. So what does this tell us? It's going from increasing to decreasing. So you're verifying first derivative test, p of 161.3 is a local max. So what we're looking for, do we need to do anything with that 162? Let's find out one more time. We wanted to find the production level that maximizes profit. So we didn't really care about the actual profit. We want to find what should we do, or how many should we make? So therefore, let's answer what the problem wanted. Production level of 162 units about actually maximizes profit. That's helpful to know. And we kind of did that by analyzing a graph this time as opposed to using the first derivative or second derivative test. And of course, you have your choice. I just want to show you how it works either way. Yes, like I know you prefer to use the first derivative test and plug things in, but I prefer to use my TI. So, okay, so we're pretty happy. You got part A, check. Part B, find the production level that minimizes average cost. Okay, so we're gonna take this part B. And let's remember what it means to be average cost. That's taking our entire cost and dividing it by how many units that we produce. So C of X over X. And sometimes people like to call this, if you want to, sometimes people will call it A of X. So if we take our cost function, which was, we have to go back and look at it, 1800 plus 25x minus 0.2x squared plus 0.001x cubed. And we divide this by x. And that was our x, that's our average cost. Now what you can do, it is a polynomial divided by a monomial. If you want to make it prettier, all you're doing is dividing by x. So you can divide every term by x to give us 1800 over x plus 25 minus 0.2x plus 0.001x squared. That is our average cost. Now, if you know you're going to find the derivative, see if you have some critical points going on, it might be to your benefit to rewrite. I see this 1800 over x. So maybe I'll take this and think about it as 1800 x to the negative 1. It helps me take the derivative quite nicely. So if I do that, a prime x, that's going to give me negative 1800 x to the negative 2. Don't have to worry about the 25. Minus 0.2. And then again, we have plus 2 times 0.001 is 0.002 with an x. And same story, everyone. You want to find critical number, you're going to set it equal to 0. If you want to, you can rewrite it so that you see that you have an x squared in the denominator. So there's a couple places what's happening. You could first figure out that, yes, we can find where our value is 0. We already know it's undefined at x equals 0, but that's not a critical number because the original function was already undefined at x equals 0. So it's not in the domain in the first place. And this is another case where, yeah, we can do this by hand if we want to, but why don't we just pull the TI out? Another way to look at it. Let me take this off to the side. Quick little graph. Let's pull up our TI and let's type it in. Again, we're looking at the first derivative. So if you want to do this, we're just analyzing. It's negative 1800 divided by x squared. Okay, minus 0.2 plus 0.002 and an x. Okay, so if we graph it, I don't know, we'll look at our past. It's a little, the window's a little wonky, so let's see. Let me zoom in a little bit. I'm going to zoom in around the origin, see if that can give me a little bit of something prettier. And yes, it's a little bit nicer. But let me point out, do we really care about the left side? What is that telling you about your x values? Left side the left branch, that's negative x's. It's impossible to produce negative units. So I believe we care more about the right side of our function. So let's adjust the window to see that. So instead of the x min, don't have to worry about it. Let's make that x max a little bit more. And I don't know, I'll do like 300. Sometimes you just want to see, do I have to go higher or lower? And sometimes if you go higher, it's easier to shrink it back down. And yeah, I'm okay. That's good enough. So I care. I'll do a quick little sketch so that you guys can see what I'm looking at. So I really am looking for this, this branch. I exaggerated that a little too much. I know it's a little more shallower. So we're doing something like this. And I know the other one's doing something like this, but again, we don't care about this because that's not in the feasible domain. So reminder, this is our derivative of our average cost. And so it's going to matter when is our average cost equal to 0? And we need to know that value, but you can tell by the graph what your derivative is doing. It's negative to the left of whatever that value is, and it's positive to the right. And so we just got to know what that number is. We know it's a nice, what does it go? What does that tell us about? It tells us about our function. It's increasing and it's decreasing. So if you go from decreasing to increasing, you've got yourself a local min. We already can verify that just by understanding the behavior of the derivative around that point. But we got to go back and find that point. Probably should have done that earlier, but sometimes it's nice to know, is it even worth it? Let's go back. So I want to calculate the 0. And I'm really so far zoomed out that I know I'm below to the left of where I think my 0 is, and I know maybe to the right. Here we go. Press the, all right, that's a little annoying, but you guys can fast forward. You have that luxury while I do this. Okay, so I'm gonna find my 0, and it's about 143.6. Cool. Go back. Mark that so you can see that. So that's 143.6. We already know it's a local min. So finally, we know we have a local min at A of 143.6. And so the production level, like they didn't really care about what the minimum average cost was. They just cared about how many do we produce before we can get a minimized cost for average. The production level we're going to probably round again. And usually I'll just round up. It's impossible to round down if you have to make a little bit more. So about 144 units is going to minimize average cost. That's where you're making the big bucks when you tell your boss this. The boss does not want to see all this calculations. And to be honest, you're probably plugging this into a computer if you're really calculating this, but we kind of know that the concepts behind it. Okay, Math 170, I know you keep hoping it's the last example, and finally we reached it. So again, I encourage you to take breaks between these. There's a lot of thinking involved. If you're tired of hearing my voice, I know you can look at your textbook, example 6 on page 264 will also kind of give you an idea of how this problem can be set up. But if you're already here, you might as well hang out. So one last problem for the section. Bear with me. I know there's a lot of concepts here, but I believe by you sticking with it and kind of seeing all the different ways we can approach these different problems, you're going to have a nice strategy when you reach problems you've never seen before. So last example. We have a hockey team. It's playing in an arena with a seating capacity of 15,000 spectators. And when the ticket price is set at $12, the average attendance at a game has been 11,000. And then they also say the market survey indicates that for each dollar the ticket price is lower, average attendance will increase by 1,000. How should the owners of the team set the ticket price to maximize their revenue from ticket sales? So there's an idea of demand going on here. And sometimes we have to set it up ourselves. And it's going to be probably with our demand function. And usually the way we talk about demand, we're looking at our price, P, that we set up for ourselves. That's lowercase p. It's a function of attendance, X. How many spectators we can see. And for purposes of this problem, we're going to assume P is linear. It's not always. But we can make that assumption here, calculus class, unless they tell us otherwise. So we've been dealing with this already. We've been dealing with, from the past example, P of X. That's what it means to be priced as a function of X. And what that tells us, when you're kind of setting up your order pairs, just so that you guys can see, function relationships. X is the independent variable, P is the dependent variable. And so there's already some things we already know about P, about the price. Is that we need to make sure that we're not going too low. You definitely want to go higher than 0, and you want to probably, if you're looking at prices, you can't go below 0 either, right? You keep subtracting off $1, you're going to run into issues of you don't want to charge, you don't want to have it to be free to get in, and you don't want to be paying people to go, and also your spectators, like you can't increase everything over to be the maximum capacity of the stadium or the arena in this case. So there are some feasible domain issues that you want to pay attention to. We don't have to think too hard about it because it's kind of set up already. But let's look at this one more time. The attendance is X. So they've already kind of given us an idea of maybe what the order pairs can be. They didn't tell us what the function is, but we can figure this out. They are saying that when the price was set at 12, the attendance was 11,000. And then the survey that they took said that if they lower the price by $1, attendance is supposed to increase. So if they lower the price, that's $11. Then the attendance would increase by 1,000. That'll bump it up to 12,000. So we basically have 2 points on the line. So if you have 2 points, you can find an equation of the line. So let's find it. First thing we probably want to do for ourselves, equation. Let's look at, we need slope and we need point. And we got the points already. We got 2 of them. So if we want to find the slope, there's your difference of the y's over the differences of the x's. Just be careful. There's 11,000 and 12,000. Sometimes that gets confusing. So what do I get? 1 over negative 1,000. And you can leave it as a fraction, but it's a nice decimal. Negative 0.001. So we've got the slope now. Now we're time for the equation. So the equation of the line, use some point slope format. I know you're used to saying y minus y1 equals m times x minus x1. But remember, we're in terms of x and p. So in this case, it would be p minus one of the points, and let's just use this one. So p minus 12 will equal to the slope times x minus 11,000. Make it a little prettier because we want it as a function of x, so we can distribute negative 0.001x. Then if we multiply 0.001 times 11,000, we get 11. So p minus 12. Add 12 to both sides. We get p equals negative 0.001x, and that's going to say 11 plus 12 gives us 23. So right now, we finally found our demand function. Now, I know that takes a little bit of work, but remember, the idea is, what do we do with that demand function? Are we supposed to take the derivative of that, or what are we supposed to do in the first place? So reading this, I'm seeing revenue, and I'm seeing that they want to maximize the revenue. So this demand function is only a tool to get to what we need to do. So the next thing we have to do is set up our revenue. And the revenue is found by, we call it R, number of units times your demand function. R equals X times P. So if you want to make it a little nicer, we already have X, and we already found what P was. Takes a little time. 001x plus 23. Okay. Well, because we want to maximize revenue, it's a function times a function, probably worth our time to distribute that x. So finally, I have negative 0.001x squared plus 23x. And that is what we're maximizing. And if we're maximizing it, we are going to take the derivative. And by now, you're probably saying, oh, nice polynomial. We could do that. So we should have negative 0.002x plus 23. It's a polynomial. We're going to set it equal to 0. That's a nice linear equation. I know it's got a decimal, but we'll deal with it. 23, you're going to add 0.002 to both sides with an x. And then if I divide both sides by 0.002, let me do that. 0.002. I have 11,500. Well, that's pretty. So last situation, before you can, sign off on everything, we want to make sure, we need to verify, is this a local max? And because we have the first derivative is a nice polynomial, it might be nice, we can actually take the second derivative really quickly, and we only get negative 0.002. That way, if you're trying to plug in the 11,000, it has no effect on your second derivative because there were no x's to begin with. It's still negative. There's no x's, it's still negative 0.002. And again, that's less than 0. And if you have the second derivative to be negative, that's telling us that the revenue evaluated at, 11,500, forgive me, is for sure a local max. Good, we verified, yes. Is that what they want? Do they want to know how many people should be there? Or do they want to know what our price should be? So let's double check. How should the owners of the team set the ticket price? So they don't care about the maximum revenue. Sometimes I'll ask a question about that. but they wanted to maximize the revenue, but they want to find the price. So problem wanted. That's why we have to always read it carefully, because, you know, so I would assume, well, maybe they want to know what the maximum revenue would be, but they actually want to know where to set the price before they even deal with that. So problem wanted the ticket price, where revenue is maximized. So we already figured out X, production level. X equals 11, well, I don't know if that is a production level, excuse me, that is the attendance. I think I'm still stuck on the last problem. That maximizes the revenue. So that's good, we got that. But the ticket price was given by P of X. So P of X, remember that equation that we just came up with? Go back. Negative 0.001x plus 23. So what are we doing? Plugging in 11,500 into our equation. And what do we get? Negative 11.5 plus 23, or if we find the answer to that, it's actually 11.5. And so that's great. You can tell your boss 11.5, but that doesn't make sense according to the context of the problem. This is where you make the big bucks. You say, boss, the ticket price should be set at $11.50 to maximize our revenue. And as long as your computations are correct, you won't get fired. But the idea is that is the idea what we're looking for. So don't assume the problem wants us to find maximum revenue, maximum profit. It's always trying to figure out what did they want from us at the end. So congratulations, Math 170. You made it through this very, very long lecture. I hope it really helps you with dealing with a lot of the different problems you're going to see. I wish you the best. I will see you in the next section.